Okay, in this talk, I want to talk about the rank ratio bound and the radius of comparison of the Cuntz semigroup. So, because while I was here, I learned that George would like to hear first the ending of the story first. So therefore, first I will list all the main theorems. And then I will get into the proof and details, and if there is any question, so I'm happy to discuss. So, okay, to somehow to give you all the main theorems, I just want to set some notations and something that I really need to state this theorem. So the first one is. I always take S as a CU semigroup, CU semigroup. The second one is I consider F of S is just the set of functionals on S. So functionals on S, they are they preserve zero. They are order preserving. This is, by the way, so I will discuss later, explain the CU semigroup. But for this one, so functionals, they are order preserving, send 0 to 0, and they also preserve supremum of increasing sequence and so on. So and then
CU function.
Yes.
To indicate is definitely jargon because it has a precise definition.
Right.
Because otherwise, you just use a word like that, someone might think that you're just looking at maps from the.
Yeah. Yeah, I think we can.
It doesn't matter, but I think in general, I mean, if someone goes to the trouble of making it precise, then I think the language should indicate that's what they're doing.
Yeah.
And not be possible to interpret just purely generically.
Yeah, that's right. So, and then the third things I want to define is rank of any x. So, okay, for any x in this or CU semigroup, so I define this function from f of s to 0 and infinity, closed interval, given by this lambda is equal to lambda of x. So for all lambda in f of s. So we call this one rank of x. So and then the next one is number 4 is for any x in the full element of S. Full elements means that the ideal generated by X is going to be the whole S. So we will define something called the relative radius of comparison to X. So, and we denoted RC of S and X. I will give you the exact definition for the radius of comparison later. But for now, if you consider the in terms of CSR algebra, so this gives for any CSR algebra, this gives you a number. So between 0 and infinity closed, right? So this is a numerical invariant. And then now, okay, now what is the question? The question is that, so suppose that you have an increasing sequence in S, right? Suppose that you have x1 less than or equal to x2 less than or equal to blah, 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 xn plus 1. And here you have x. X is going to be sup of these elements, x. If you have an increasing sequence in your Cuntz semigroup, then for the radius of comparison, you have a decreasing sequence. So you have this RC of S relative to X1 is bigger than or equal to RC of S relative to X2, and go on. And then here RC of X, S, and Xn. And here you will have RC of S and Xn plus 1. And at the end, you have RC of S and X. So we can easily prove that without by some elementary calculation and definition of the radius of comparison. And now one may ask that, okay, so this is increasing sequence. So can I compute the limit of RC of S and Xn? And goes to infinity. So can we say that at least in some cases, under some condition, do you think that we can obtain this is going to be RC of S and X? So to answer this question, so we have to define something called the rank ratio or rank ratio bound for any X and F. For any pair of elements in our Cuntz semigroup. Okay, what is the rank ratio now?
I thought you said you were going to give the statements first.
Yeah, but I just want to prepare the ground for.
You're hiding the statement.
So I give you a statement in a sec.
Huh?
I give you the statement in a sec. I give you the statement in 2 minutes.
Well, clearly the only reason to give definitions before the statement is that you can't understand the statement without the definition.
Yeah, but I think at some point I should say that if I use in my statement, if I use RC of S and X, so nobody knows. So what is RC? Okay, not nobody, but there are some people they might be surprised.
But so you didn't define that.
No, I didn't define. I just say that this is just numerical. I will define it later after listing our main theorems.
Okay, but if there's something which is actually true involving it, then people will be interested in seeing the definition.
Yeah, this is actually, I should have said, this is the question now.
Well, this is the question.
Yeah, this is the question, and now
You have a question.
yeah. So okay, because this is not true always, so I have to put some.
Oh, I see.
Yeah, I have to put some condition on the rank ratio, and then that would be true in that case. So okay, as I said in the title, so what is the rank ratio? So for any X and Y in S, so rank ratio at X and Y denoted by rho of X and Y, and this is equal to inf of all R bigger than 0, such that rank of X is less than or equal to R dot rank of Y.
Okay, but you're going beyond just talking about the rank ratio. It seems to me you're measuring it. You're measuring the rank ratio.
Yeah, this is kind of bound. This gives us the kind of control for ratio of X and Y.
Yeah, I mean it's 99% just the soup of the ratio. Right?
Yeah. So this is the definition, and now the main theorem is here. So the first theorem is this theorem. Okay, S is a Cuntz semigroup. S is a CU semigroup. And then we have elements Y and the sequence YN in full elements of S. And then what else I have? Oh, okay, with this, those are increasing with that. Yn is less than or equal to yn plus 1. This is less than or equal to y. So I also have one more condition that this is not empty. So what that means, so we know that f of s, it means that all CU functionals on S. And if I put y, it means that all CU functionals which are normalized at y. Because, for example, here, this can be a functional. So this can be functional. For example, we denote it by lambda infinity from S to 0 and infinity, such that lambda of 0 is 0 and lambda of A is infinity for any A in S except 0. So those are not normalized. So, but here I assume that I at least have one normalized CU functionals at y. So, and I need one more assumption, which is this: limits of rho of y and yn is less than infinity when n goes to infinity. So if I have all this assumption, so then, okay, then what is my main theorem? The main theorem is that limits of RC of S with respect to yn, n goes to infinity. This is less than or equal to limit of rho of y and yn, n goes to infinity times RC of S and y. And here, this is here I have this lower bound, 1 over limit of rho of y and yn, n goes to infinity, RC of S with respect to y.
When you say the limit of the rho, so finally, I don't know if you said that the limit exists.
So in this, when I have such situation, when I have this one, so the limit exists. So I consider sometimes the limit can be infinity. So I assume that the limit exists. So
no,
okay.
Yeah. Infinity is a
Okay.
value of the limit.
Yeah.
But I mean, I wouldn't mind if it converged to infinity, but for something to converge, I mean, not just an arbitrary sequence of numbers will converge.
I think I want to draw your attention to this fact that I said here. So if you have an increasing sequence, so RC is going to be a decreasing sequence, which has a yeah.
If it's just the sequence, it's just two elements, no, but that's this. You said for RC, but you didn't say for rho. So
oh, okay, yeah.
That requires people to put on their thinking caps.
Yeah, I think this is a good question. So I would say that here this rank ratio has some basic properties. So this rank ratio is kind of, this is monotone on here. So let me say, maybe I can add here. So if I have this, then rho of y and here I have x. Sorry, I have say that rho of x and x1, this is bigger than rho of x and x2 and blah blah blah. And also I have one more thing. If I change this, so if I change this rho of x1 and x, this is less than or equal to rho of x2 and x and blah blah blah. So therefore, this sequence I have here, this is decreasing, right? So therefore, and because this is finite, because this limit is finite, therefore the limit really exists.
Well, if it's decreasing,
decreasing and lower bound 0,
no,
and bounded.
I don't understand. You're saying the sequence is decreasing.
Yeah.
Well, then saying it's saying that it's strictly less than infinity is an independent statement. Nothing to do with the limit.
So the point is that I didn't want to end up because those can be all infinity, right? Those can be all infinity. So those all this rank ratio, so they can be all infinity. So I don't want I want to avoid that, right?
Well, why not just say that? It's rather complicated to say the limit is finite when it's a decreasing limit. It'd be enough to say the first term is finite.
This is part of our assumption. So, and then I will explain when I want to get into the details.
When you wrote that on the board, first of all, no one had any idea what you mean by the limit. But secondly, it seems that since it's decreasing, we don't need to worry about the limit. It's enough to look at just a single term.
So, okay. If this limit is infinity, so then what I can do?
I'm being sticky.
Right.
You don't in a general introduction, you don't want people to worry about facts.
Yeah. So, yeah, but I have two cases. I will explain later. So,
Well,
in case that this is
any
infinity.
Explanation is needed. I was just trying to find out what you were talking about.
Yeah. Okay, now.
It only took 2 seconds, if they were the right 2 seconds.
Okay, sure. So, any further question about the statement of the theorem?
What's the statement of the theorem?
If we have that assumption, CU semigroup, then I always have a bound for the limit of the relative radii comparison. So I have always this limit. For example, if this limit is equal to 1, therefore this is going to be equal to 1. Sorry, I think here it should be y. Sorry, y. So if this limit is equal to 1, therefore this has to be 1. Therefore, the limit of this relative radius of comparison is really equal to RC of S and Y. So it means that
you're jumping again. You're saying if one limit is equal to 1, then the other limit is also equal to 1.
Yeah.
Well, you didn't even say that, but that's fine.
Yeah.
Good.
So therefore, that's why I somehow put a question mark right there. So in general, it's not true that this limit is equal to this one. So, but if the limit of rank ratio is equal to 1, so therefore here I have RC of S with relative to Y. Here I have RC of S relative to Y, and then therefore this limit is equal to that. So, what else? So then, considering that, we also define another define another function called the radius of comparison function. What is this function? It's just simply RC of S and dot. So associated to any, we can define this one, this radius of comparison function associated to any Cuntz semigroup. So but here from full elements of S to 0 and infinity. So simply by X maps to radius of comparison of S and X. So now the question is that what is the range of this function? So now in lemma 1, we prove that lemma, if you have a CSR algebra A, which is unital, simple, probably, yeah, stably finite, with this condition, with RC of CU of A and identity is equal to 0, right? Then what we have are RC of full RC of CU of A and full elements of S. This is going to be 0. It means that if you have a 0 radius of comparison on unit, therefore you can get 0 radius of comparison on all the full elements of S. So, but one may ask that, okay, now what if the radius of comparison with respect to unit is not 0? So what do we have? What is the range of this this function in that case? And here we have another theorem. Theorem. A is again unital, simple, stably finite. I don't need simplicity here because I proved this theorem for non-simple CSR algebra as well, but I just want to stick with simple for now. And then suppose that radius of comparison of CU of A and unit is equal to R for some R in 0 and infinity. So then the range of radius of comparison function, associated to CU of A, CU of A. So here, sorry, here I should have said S, I meant CU of A. So this is going to be 0 and infinity. So it means that if you have if radius of comparison with respect to unit is equal to R, so then you can manufacture for any number in this interval, you can find a full elements here such that the radius of comparison relative to that element is equal to this. So by the way, so here I need one more assumption, namely plus a stable rank 1. Stable rank 1, because in the proof of this theorem I use the positive answer to the rank problem for a stable rank 1 CSR algebra. So you may ask, okay, what else?
Ali,
So and
can I ask you a question about your theorem?
yeah, sure.
So you say that by choosing a full element, you can make the range of your function to be 0 infinity, certainly not include infinity, but can it really include 0?
Okay, you wanted to ask a question about this last theorem, yeah. Infinity is definitely not included, so it's closed. It's an interval. 0 is closed, but infinity is open.
But how to include 0? It sounds like you take a non Z absorbing C algebra, then look a hereditary subalgebra, then the hereditary subalgebra is Z stable. It's
oh no, I think actually I think constructing 0 is the easiest part. Why? Because if you take A to be infinity dot identity, right? So if you take this one, then we know that RC of CU of A with respect to infinity identity is less than or equal to 1 over n RC of CU of A with respect to identity, right? For any n.
Yeah, but what happened on C algebras? I mean, let's take A to be the Wheelerson algebra.
So okay, A to be Wheelerson algebra. Okay.
Then you take
And the
some
RC, the
element.
radius of
Looks like you are taking something like hereditary subalgebra, but no.
No, I'm changing the full elements here. So suppose that let's stick with the example you made. So suppose that you have a Wheelerson algebra,
Yeah.
and the radius of comparison with respect to identity of that CSR algebra is R, and this R is a number between 0 and infinity, right?
Yes, but for which element the radius of a comparison with Wheelerson algebra is 0? That looks like you are talking about some kind of a strict comparison.
A strict comparison with respect to this full element, because I'm changing the full elements. Here, I'm saying that for give me a number, give me any full, give me a number right here in this interval. I can give you full elements, right, in the Cuntz semigroup of your CSR algebra.
This full element actually has rank infinity.
Sorry, say it again.
Well, does this full element has rank infinity?
Yes.
Okay.
For 0, yes. For zero,
yeah.
Because if you consider this one, if you consider A to be infinity dot A, the fact is that for every lambda, I can write it here.
But then you are looking at the infinity plus something compared to infinity. Then
so here, for example, because here our CSR algebra is simple, just consider this one infinite, right? So this is going to be infinity. So and then RC of CU of A with respect to infinity, because RC with respect to identity is finite, this is going to be 0. And the proof is also pretty easy, because for any functionals non-zero, lambda of infinity is going to be infinity, right? So therefore, I have what I can get. Therefore, this implies that for any n,
so
lambda of identity, right? Identity is less than or equal to 1 over n lambda infinity.
So this radius of a comparison is never a radius of a comparison of some C algebra. I mean, it's some C algebra related to the algebra you start with. For example, the Wheelerson algebra. It cannot be.
It cannot be 0.
Maybe you want to maybe this is a good point to give the definition of the RC.
So yeah. Okay, yeah. I think here, just last comment. So here you should take into consideration that I'm considering the relative radius of comparison, not the conventional one.
I don't see what difference that makes.
So the difference is that the conventional radius of comparison, the full elements is always identity, right?
Yes, but that's relative to the identity.
It's relative to identity. That's right. But here, I'm considering all full elements, not necessarily identity.
You're considering some particular full element. No, there's no difference. Logically, there's no difference. What's causing the difficulty is that usually what's usual is that the radius of comparison is relative or not. What's usual is that you're working with respect to a projection. But as soon as you go to a positive element, then that positive element might be a strictly positive element for the stabilization.
That's true.
What you're talking about.
Yeah.
So it's nothing to do with arbitrary full elements. except that insofar as you're not requiring them to be projections anymore.
Okay.
Well,
Yeah.
isn't that
So
right?
that's the, so okay, then let me just
What that means is that the radius of comparison is not a reliable indicator if you don't stick to projection.
why is you can
Because
take
you're-
any.
all of a sudden, out of the blue, when it was with respect to a projection, it's non-zero. All of a sudden, out of the blue, it becomes zero, but that's very misleading. Usually, people think of zero as meaning the thing is well behaved, but it's not, it's still the same badly behaved algebra.
I think here you should only determine what kind of full elements you are talking
Yes,
about.
Yes, but my point is there any advantage whatsoever any time in the world looking at non-projections?
So yes,
can we
because for
take-
example, just take C M2 of C of X.
Take which?
Just take A to be M2 of C of X. Just take A to be M2 of C of X.
We're not looking at simple algebra.
I mean,
Okay, fine.
so that's probably not a big deal. So yeah, the general theorem is for residually stably finite with. Okay. Now, suppose that you have two elements A. One is okay, just to make it more simple. Closed interval 0 and identity, right? So sometimes you want, this is a full elements, right? This is also a full elements. X minus 1n identity of A. Identity of C of X, sorry. Identity of C of X. Now you can consider the radius of comparison with respect to this full elements, or you can also consider the radius of comparison with respect to these full elements, even for any n.
What's this x minus 1 over n?
This is sorry, positive part. Yeah.
But they have finite rank.
Why they are not finite rank? You can compute the rank ratio of them easily. So here, for example, if you compute that one, so you can compute the rank ratio of A and AN is equal to A and AN is equal to 1, and the rank ratio of AN and A is equal to 1/2. So therefore, you can, this is literally the definition of Blackadder, Wilhelm Winter, Tikusis, and who and other, I think, Leonard Robert, who they define the algebraic relative radius of comparison. So, is there any?
I thought the question was why the radius of comparison was interesting for a non-projection.
So, okay, so you can say that what is the radius of comparison with relative to this? What is the radius of comparison with relative to this for any n? And what is the limit of the relative radius of comparison and connection with this? So, and this is the main question that we want to reply in the main theorem.
But that's not a reason for the non-projections to be interesting. That you don't know something. You're saying you're going to ask a question for non-projection.
So for non-projection, I don't know, from people who are working in radius of comparison, this is full elements, and this case is also interesting. So,
But they are still compact element. In the example in the board above, actually, it's a non-compact element. You have infinity rank.
so this is not compact, but you can still find a finite radius of comparison for that. You can compute the radius of comparison with relative to A, and you will figure out that this is finite for this CSR algebra. So,
Okay, but what's interesting about projections is that I mean, if you don't, even if you don't have one which is singled out as the unit, then if the radius of comparison is non-zero for one projection, then it'll be non-zero for all non-zero projections. But if you go beyond projections, the more general full elements, it looks rather erratic. It seems to me that before you can say it's interesting, you have to find some interesting pattern.
okay, what if your CSR algebra is stably projectionless? Isn't that interesting to look up those radius of comparison if you don't have any projection?
Okay,
And there are many examples of that.
but then you can have if it's a finite non-projection, then you can have a non-zero radius of comparison.
Yep.
But if it's the infinite element of the Cuntz semigroup, then it's always zero.
If the radius of comparison of this one of the elements is finite, yes. If not, the only thing you can say is this inequality.
My question was, is it always zero when you put in the infinite element?
No, it's not always zero. There are some examples. I don't have the examples now, but there are some examples that the radius of comparison relative to infinity is not zero. It's infinity.
What about relative to a finite? No.
Relative to it depends on the rank ratio of this function.
Anyway, maybe there are some interesting patterns.
Yeah. So maybe the interesting part, which is somehow gives you a connection between what you and Young actually at some point with someone else define is something called the oscillation of elements, right? So now what I want to say as a last theorem I prove is that what's the relation between this rank ratio bound and oscillation of element, and here is the theorem. Maybe I can erase this part. So if you have a CSR algebra for any element positive in a matrix algebras over A, and from 1 to infinity. So here A is a very nice unital stably finite CSR algebra. Oscillation of A is denoted by omega of A, which is equal to sup of d tau of A minus tau of f of 1 over n of A. And here you take sup over, sorry, here you have limit, by the way. Omega of A is equal to limit n goes to infinity. Here, all normalized traces. So what is d tau of A? D tau of A is just limit of tau of A to 1 over n goes to infinity, right? And what is this this function f with 1 over n? This is just this function. Here you have 1 over n. Here you have I think 2n, right? And here you have this function. And here you have 1. So you have 1. So this is called oscillation of element. This oscillation gives you somehow a jump in your rank function relative to A. You remember drawing this oscillation of element in your paper?
Well, I never use oscillation. It's just
Then why did you
the
define
trace
it?
being uniformly small
Yeah.
and the
Okay, but
continuity of the rank function.
yeah, this is actually, I would say this is one of the interesting things which is related to continuity of the rank function. So, and here is the theorem we proved, theorem. So A again is a simple unital stably finite CSR algebra, and you have full elements in your matrix algebra.
Some papers of Schwan Long and
Yes.
Chen
Yeah.
talk about oscillation.
Yeah, but the original definition was given in your paper with Zhuang Niu and someone else. The original definition, and they somehow provide some connections between oscillation 0 and a stable rank 1 and the stability and so on. So okay, and now here what we want to say is that number and then okay, if we have this, then full, then the following are equivalent. So number one, limit of the rank ratio function is equal to 1. This limit, when n goes to infinity, this is equal to 1. Number two, oscillation of A is equal to 0. And number three, the rank of A is continuous on the on normalized function. Yeah, this is a good question. So I haven't checked, but it might be true. So CU of A. And this is basically the whole.
What if you normalize at some level in the full element?
So there is a bijection map between if you normalize on 1 and if you normalize on some other elements. If you just divide it, if your CSR algebra is pretty nice, there is a bijection map between that. I assume yes, because you just multiply by one scalar.
Oh. Yes.
Yeah.
But it's difference between one projection and the other shouldn't be very serious.
Yeah. But here, if there is, because the rank ratio is not always 1, so so this theorem tells you that if the rank ratio, so if you, for example, have this this diagram, so suppose that you have something like A here, and here you have a something like that, right? There is a jump here, right? So here you have jump. So if the limit of such jump is equal to 0, this is equal to continuity of day, which is already known by the result of Shuanglong and Hua Shenlin. And now here we say that this also is equivalent to say that the limit of rank ratio is equal to 1. So okay, let's.
But in fact, you know, this property. Let's look on the C algebra level. It's really talk about the neighborhood of 0 has uniformly small trace. But if you are looking at the rank ratio, then then you are comparing the trace of the whole element A and I mean the rank of the trace, and compare it with the trace from 1 over n to 1. But because the neighborhood of 0 is uniformly small and all traces, then yes, the ratio should be
Well,
yeah.
Yeah.
Well, I mean, just to try to give an explanation in the
right.
using traces.
What's this an explanation of?
The role that ratio.
The explanation that when we have oscillation 0, why this ratio should be equal to 1. So Zhuang is saying that when this oscillation is 0, it means that it's uniformly small around 0. And when it is uniformly small around 0, this is therefore the ratio should be equal to 1. So therefore, you can discuss about the radius of comparison relative to those elements. But if you have oscillation non-zero, so how are you going to? You may have some problem to talk about the radius of comparison with two elements in which the oscillation are not zero. But we somehow interpret it in rank ratio and then give you some relationship between relative radius of comparison and rank ratio or rank bound. Do you still have question, Zhuang, about this theorem?
Oh, actually, yes, about this theorem and compare it with the later theorem. The later theorem, A is always in a matrix algebra, so A cannot be infinity.
So
Because-
okay, here's the point. So
you
can find
A always has a finite rank, so you cannot use this A to get something with
no,
some version
the point.
of zero radius of comparison for some non-Z stable system algebras.
No, that's okay. So this is one point, and the other point is that here I use the algebraic radius of comparison. So if you have a definition of algebraic radius of comparison, then your full element can be infinity. But if you have a unitar residually stably finite C-star algebra, and if your rank function is finite, therefore it doesn't matter. You want to consider the conventional radius of comparison or the algebraic one. But here in this definition, yes, I am allowing A to be in CU of A rather than in W of A. So, okay, I want to wash my hands and then get back to you again.
Respect to projection, is that going to be the same as the regular rank of comparison of the cut down algebra? Is that true?
No, because if you cut down it, you don't know what the regular rank is. You cannot compare it. So you can, the only thing you can say. So first of all, by cut down, it means that this, right? This is.
No, respect to projection. Not a. I'm looking at rules of radius of comparison with respect to projection, not a.
Okay.
Yeah. So I have a cut down.
You have a CSR algebra. You want to cut down the CSR algebra with the projection, right?
Yep.
And now you want to talk about the radius of comparison with respect to this projection.
Asking the question. So if I have a projection
Okay,
Raster algebra, I have a cut down algebra. That algebra has a radius of comparison,
yes,
right?
yes.
It doesn't, at least maybe I'm missing something, but it doesn't have to be the same as the rank.
No.
As radius of comparison to figure out.
No, we have a certain formula defined by this rank ratio things for the radius of comparison of corner. This is a corner of your
Yeah,
or
yeah,
on there.
that's-
So yeah, this is RC of this corner is less than or equal to 1 over 1 over inf of tau of p for all tau in here, RC of A, and it's bigger than here RC of A, but here 1 over sup of these things.
And how does it relate to RCA with respect to P?
So this is basically a matter of traces. When you normalize traces, so here when you consider radius of comparison of this one and you want to talk about the radius of comparison of this, you are considering normalized traces on P.
Yeah, this inequality doesn't confuse me.
Yeah.
I understand.
Yeah.
Well, look, if you take the radius of comparison of PAP with respect to P, isn't that going to be the same as the radius of comparison of A with respect to P?
Yeah, because if yeah, yes, because P is full, therefore RC of CU of PAP with respect to P is equal to RC of CU of A with respect to class of P.
It's the same as CU, really.
Yeah.
Oh, sorry, I guess, right, you're also saying that.
So this is a matter of you are using the, I mean, yeah. Okay, so let me just give you the definition and then I will.
I don't.
If you consider, yeah, the problem is that, so if you consider this one, this is based on CU, not based on A, right? So therefore, CU is always invariant, is not changed over matrices.
But are you saying that RC of A and RC of CU of A are different things, or what?
RC of the full corner,
So,
RC of full corner with respect to P is equal to RC of A with respect to this. But here, okay, maybe I can translate this one. This notation here, it means that RC of P, A, P with respect to identity.
Yeah, yes, that's how I.
Right?
I interpreted it. Yeah, so
And
how
here-
is it related to RC of A to RC of A with respect to B? How is RC of PAP related to RC of A with respect to P? That's my.
It depends, you normalize traces on A or on P.
I.
Here is always P, but
I'm
here
not
is
doing anything.
identity.
It's your definition. Are you normalizing or are you not normalizing?
I'm normalizing, but on identity.
Okay, and when.
Because the point is that if you have this one, if you have all functionals, for example, let's say identity of CU of A by and then this one, for example, all functionals but normalize and the other one, normalize and another full elements, right? So there is a bijection here. This is bijection, and then what you can do, you can, because this is full elements, right? Therefore, lambda of A cannot be 0 if you are among normalized one. So therefore, if you just divide your trace, if you normalize it by lambda of identity, you are done, right? Here, lambda maps to 1 over lambda of A, lambda, right? Now this is normalized. So now it depends. You consider normalized here, or you consider normalized here. If you consider normalized here, you have this scalar, right?
That answer my question.
Mm-hmm.
Again, my question is, well, I'm just trying to understand. I mean, you can write out the definition, I can think about it, but think it might be easier if you just tell me. So I'm looking at this RC of PAP with respect to the unit.
Right.
What do you, when you write that, what do you mean the unit of A? The unit of,
It means that I consider all functionals normalized at 1, right?
You're supposed to assume to have a unit.
okay, and then it has the unit in the corner.
Right. Whatever I am writing, and I'm considering the radius of comparison with respect to whatever here, it means that I consider all the traces normalized at this one.
And then I have another quantity, RC of A with respect to P.
Yes.
Is that the same thing or are those different?
Are you comparing with this or no? Are you comparing?
So that you're taking with respect, I just don't understand where there you're on the left, you're taking it with respect to the projection and not with respect to the unit in the algebra.
So because I changed, because I want to say that the relative radius of comparison. First of all, this part is always regardless of the radius of comparison. If you have a full projection, this is always isomorphic to CU of A, regardless of any radius of comparison or on anything. So, so if you have a full corner, then CU of full corner is isomorphic to this. So therefore, I'm just saying that this is isomorphic to this. So those relative the relative radius of comparison with fixed projection is the same. I mean, to be honest, I don't think that it's related to radius of comparison. It's related to Cuntz semigroup, I would say.
Oh, so you're saying taking radius of comparison with respect to a full projection is in fact kind of useless because it's going to be the same thing.
Well, it's
It depends. If you consider
it would always be a finite
yeah.
relationship
That's right.
because the rank of a projection is finite valued and continuous, and so the rank ratio, the ratio of the ranks of two different projections will be a bounded function on a simplex, on a compact subset of the cone.
Okay, but what if I take not a projection, but I take some positive element and I look at the corresponding hereditary subalgebra.
Mhm.
So what can you say about that?
So this is, so I think because if this CSR algebra is full hereditary, I think again we can say that the cone semigroup are the same. If you have a full hereditary CSR algebra, right? Then CU of A and CU of, let's call it B, they are still the same, right?
I guess what I'm trying to understand, so these numbers, so in that theorem at the end, so you say that these numbers can be anything. Like you can find for any, pick any number, you can find a full element such that
Yes.
that will be that.
Right.
What is the meaning of that though? Like what does that mean? Like what is the meaning of saying that radius of comparison of CU of A with respect to some particular full element is equal to some number? What does that mean on the level of the algebra?
At the level of algebra, it means that how far this CSR algebra is from being classifiable. If it is 0, it means that this is we are done, so it's classifiable.
No, I know what radius of comparison is, but I'm talking about the relative one. Like I know that radius of comparison equals 0 means that that's stable. I
Right.
understand that part.
So
But
Well, everything is relative, and you should just keep
Sure.
emphasizing what it's with respect to, what is relative to.
So for example.
so let me just give you a,
You start out with a C-star algebra with those conditions.
Right.
With radius of comparison equal to r, so it's and not equal to 0, so particularly
Right.
not classifiable.
Yes.
Not that stable.
Yeah.
And you're saying that you're looking at full elements, and you can, for any number, you can find a full element to get any possible radius of comparison.
yeah,
Can you, does that say something like, oh, I have some sort of subalgebra, some kind of subalgebra sitting inside of my original algebra with a different radius of comparison? I don't understand.
no, I don't
the
say any,
level of the algebra.
no, I don't say anything about the level of algebra because the CSR algebra is fixed here. So I have just one CSR algebra, which is A, and I only consider CU of A. I don't consider anything. The thing is that the fact is that I'm changing these full elements, and I'm considering the relative radius of comparison with respect to full elements.
Like, what does it mean? Like, why is this? What does it mean that you can find an element such that, so maybe you started with radius of comparison 1, and then you're saying you can find another full with respect to the unit, and then you're saying you can find another full element such that the relative radius of comparison with respect to the element is equal to 2.
Yeah.
I can't fit that in. Like, I don't understand what that is saying. What is that telling me about the algebra or about the Cuntz semigroup? I don't quite understand the.
Okay, what the radius of comparison is telling. For example, if you ever want to give you a very simple example, so suppose that you have RC of M2 of A with respect to identity, and suppose that you have RC of M2 of A with respect to identity of M2 of A, right? So this, okay, what this means that this is equal to 1/2 RC of A with respect to identity of A. So for example, so you take this element, another one take this elements, now I compare.
Computation now, that's not fair. You haven't even given the definition. How can you
Yeah,
follow it?
okay, sure, because I wanted to answer this question, that's different.
It doesn't answer it if you just.
But I know how to do that computation, so I'm
Yeah.
okay with that. But I still don't, I'm not sure I understand the.
Because radius of comparison is a relative one, is just a numerical invariant, depend on the what kind of full elements you are considering. For any full elements, it gives you a number.
RC, respect to the unit,
Right.
is telling you how far it is from being Z stable.
Z stable,
And,
right?
like, I mean, that doesn't
No, but
have any formal meaning to
Look,
it.
Right.
But,
If you say any projection instead of the unit, then it will give you exactly that information.
sure, yeah, but as we talked, taking it with respect to projection, it's kind of redundant, no?
Well, you're
Yeah, I think that if you take projection, so projection is always less than or equal to identity, right? This gives you this relation, RC of A with respect to identity is less than or equal to RC of A with respect to P. So if this is 0, therefore this has to be 0. Therefore, that's why probably George is saying that just consider projection, right? For any projection.
Well, that's not so much, it's not exactly what I was thinking. What I was thinking is that the rank of a projection is a continuous finite non-zero valued function. And so if you take the rank ratio, what you in the technical way call the rank ratio, in this case actually is just the ratio of the two functions.
Oh, okay.
And it's a bounded function, it's a bounded finite valued function. And that, so the soup will be a finite number, finite non-zero number. And so then that means that if you look at any two projections, the different RCs will differ by a finite non-zero factor. That's what I think that's what I think that's what Fuller is wondering whether that's true.
Yeah, okay, I can give you another example. I think I erased it, but you see, for example, suppose that you have these elements. Suppose that you have take A to be X identity, and B to be, for example, identity, and this, right? Suppose you consider this. So if there is a okay, and now both of them are full, right? So now if you want to compute the radius of comparison with respect to B, you can easily compute this one. But this one may not be easy. But the fact is that using this rank ratio machinery, you can at least find the lower bound and upper bound for the radius of comparison with respect to this element.
Okay.
Right?
I understood that. That part I'm okay with.
Mm-hmm.
But what is the interpretation of the radius of comparison of CU of A with respect to some a non-unit or even a non-projection?
So
what is that measuring?
this is measuring of
If I'm measuring with respect to the unit, I'm measuring how far away it is from being z-stable. If I'm measuring with respect to not the unit but something else, what am I measuring?
so here it depends. Based on the theorem, we prove that there. So if, for example, when you have a z-stable CSR algebra, it means that the radius of comparison is always 0, right, with respect to unit. And then we prove.
Doesn't cover it because
Yes.
theorem is only for non-zero.
Yeah.
I'm asking for a non-classifiable.
For non-classifiable CSR algebra, you can compare the rank, how far the rank of elements are with respect to the rank of these full elements. So let me give you the give you the definition for the radius of comparison. So that's probably makes everything clear. So definition. So again, S is going to be a CU semigroup. CU semigroup. So for any R in 0 and infinity, so we say that and okay, here I need one thing probably. So here, suppose that X or maybe E. So E is a full element, right? S. So we say that S and E as R comparison. If whenever X and Y in S satisfy what? Satisfy rank of X plus R rank of E less than or equal to rank of Y. If you have this, then this implies that X is less than or equal to 1. And now the radius of comparison of S with respect to E is just inf of R in 0 and infinity such that S has or maybe S and E, sorry. S and E has R comparison. So now, so here this is a full element. So you are somehow comparing the rank of two elements, but not necessarily with unit, with something else. So that result, I mean,
What does that tell you?
so this is because this is for non-classifiable CSR algebra, so therefore you cannot compare this result for classifiable one. For classifiable, this is always 0. But for non-classifiable, for example, let's consider M2 of C of X, right? M2 of C of X. So you can consider different full elements and then compute the radius of comparison.
And you're telling us that the image is going to be everything under these conditions.
Yes. It means that you can manufacture all these elements. So if you
I'm not so the experiment. I guess I'm asking you to give some sort of interpretation. Like, what is this telling us about non-classifiable algebras? Like, was this unexpected, or like, did you expect the image to only be a certain set of numbers but not others, or I just can't
Well, it doesn't seem to distinguish between classifiable and non-classifiable.
No, you're asking for the radius of comparison to be non-zero, R to be non-zero, so
Oh.
R non-zero means non-classifiable.
Oh, yeah.
For example, if I want to make it clear as an application of this theorem, you remember the talk of Chris that he somehow provide a class of CSR algebra, family of CSR algebra, all has a stable rank 1 with the same radius of comparison, but they are non-isomorphic. So if you take all this CSR algebra, so that Villas-Ten CSR algebra, so then you can even claim that the radius of comparison function, the image of radius of comparison function is going to be 0 and infinity, not necessarily one single number. Because those CSR algebra, all of those CSR algebra has unique radius of comparison, which is, let's call it W, right? And this radius of
So can you start again? Because at some point you said Chris's example, and at some point you said Villas and algebra, which
I mean, those are Villas-Ten algebra actually. So, but
Well,
the same radius of comparison. So what they constructed, this is a type of Villas-Ten algebra.
type. But when you say Villas and algebra, I'm thinking of George's and Zhuang's result that Villas and algebras are now classifiable, assuming you have the radius of comparison covered. I mean, you're also.
With a fixed base.
I mean, you're assuming that the base is fixed and their base, I think their base is also fixed.
I mean, it's I think George, they have some kind of K contractibility or something,
But it's a very.
but they
No, no,
didn't.
no, But the difference is whether there's just a single matrix algebra at each stage.
Or a sum, and they take sums, I believe.
Yeah, I think so.
So, but going back to that example, so they provide an example of C2
Mhm.
algebras, not classifiable ones, where the radius of comparison is the same,
Right.
but they're not the same because they look at this sort of local
Yes.
radius of comparison.
Yeah.
I don't quite remember how that works.
This is exactly this. Local radius of comparison is nothing except the radius of comparison with respect
But
to.
they produce two algebras such that their local radius of comparisons are different, which allows them to conclude that they're not isomorphic.
Yeah, I
But
know,
Here you're
but
saying that.
no, listen, they somehow
We're
compute,
talking about the unital algebra.
they consider radius.
When they find a different, when they find a different, they cut down to a different projection. They're then looking at that unital algebra.
Yes.
Well, then the radius of comparison is for the unital algebra is different. But of course, with respect to the given, I think it's just as simple as that with respect to the given, well, maybe I'll have to check if it's absolutely with respect to the unit of the fixed projection. All the other cut down algebras would have the same radius of comparison because you stabilize.
So here, maybe in our setting, what they compute is the radius of comparison of this unit of CSR algebra. What is the unit of this CSR algebra? It's just this P, right?
Yeah.
So, and in our setting, what is this? This is just radius of comparison with respect to P,
Sure.
right?
Yes.
So, therefore, this is just they somehow indirectly use the relative radius of comparison, not necessarily.
That's
Yeah.
precisely why I'm
Yeah.
confused by this result. So in their setting, they're saying these two algebras, even though the algebras themselves have different radius, have the same radius of comparison.
Yeah.
They're still not isomorphic because this local radius of comparison is different. But
Yeah.
here you're telling.
No, the radius of comparison of all of them are the same. The radius of comparison of their result are the same.
Everything is relative. You have to say what the full.
Oh, okay, sure.
They produce non-isomorphic algebras with the same radius of comparison.
Yes.
And
Well, that
they-
means-
Let's call it W, right?
With respect to a
There's
fixed,
two algebras.
that
It's
means
not
with
one algebra, it's two algebras.
Different non-isomorphic unital algebras with which have the same radius of comparison with respect to a fixed projection in the stabilized algebra.
Yeah.
That's my understanding. So they all have the same stabilization.
You know, they
Yes,
have,
yes, yes.
you see, they have, for example, TP1, and the other one is RC of QAQ with respect to Q. But those are equal, and those are equal to W or something. You know, the radius of comparison of all of them are the same. But the Elliott invariant are not the same for that type of velocity algebra.
When you say the radius of comparison, you insist on saying it in a confusing way. What you mean is
I mean, with respect to Q. Here, I meant with
Sorry?
respect. Here, I meant that with respect to Q, with this projection. They found two full projection, P and Q, and then they consider the radius of comparison with respect to those different two projection. They claim that those are equal, but the but the Elliott invariant of those CSR algebra, this one and this one, are not the same.
It's hard to follow it.
I think I shouldn't somehow get into details of their work.
I thought I said it and I understood it, and you then resaid it your way, and I didn't.
Okay, so I think we are saying the same thing basically.
Well, why don't we say it then?
Sure.
You never cut down. You never cut down. You look at the stabilized algebra, and the point is that if you look at a fixed projection in the stabilized algebra.
Yes.
And then you look at different cut downs, but you don't really. What you do is in the stabilized algebra, you look at different projections, and of course the different projections will give you different relative RCs.
Yeah.
But then when you're finished, you point out for each of those projections that is the unit of a certain algebra. They made the cut down. So at the very end, you talk about the cut down.
Yeah.
Well, anyway,
Okay, so,
Yeah,
so
this-
are you
mhm.
saying that are you saying that this phenomena that Chris and Elon found is somehow, let me try to interpret like this result. Are you saying that this is sort of this is the norm? Like, so you're saying here that if you're taking like you're taking your algebra A with a non-classifiable, so with this radius of comparison, and you're saying that, well, not quite, you don't look at projections, but you look at full elements, and
Yeah.
you're saying that you can always find, well, at least not, well, much more than that, but you can at the very least find two full elements.
Yeah.
Such that corresponding radius of the relative radius of comparisons are different.
Yes.
So. But it's not related to the algebra though, so I don't.
Yeah, the algebra is fixed. So it's like for example that the theorem proved by I think Andrew Toms or maybe Vilas, I'm not sure. So if you give me any real number, I can give you a Vilas-Sen algebra in which the radius of comparison that of that Vilas-Sen algebra is equal to R, right?
the only algebras that would be different with your, you know, I really get messed up with these non-projections because in that setting, the only algebras you'd be saying are different are non-unital algebras. You'd be saying you look at the stabilized algebra, then you look at different full elements, which non-projections that's the innovation in your approach, it seems to or part of it. But you're looking at the different non-full elements with respect to which there are distinct values of the relative radius of comparison. But then when you cut down to those elements, then you're getting non-unital algebras now, which are, if you calculate the radius of comparison with respect to not with respect to the unit of the algebra, but with respect to the full element that corresponds to the class of the algebra. It's not the infinity, but it's a strictly positive element for the algebra itself. Anyway, if it were a projection, then we'd be talking about the usual radius of comparison with respect to that unit of the cut down algebra.
Yeah.
Radius of comparison with respect to the unit. But as soon as you start looking at non-projections, then this the idea of different radii for comparison with respect to the relative full elements. It's a bit like apples and oranges, because the algebras that you're comparing in some sense different are the ones that have these different full elements as 50 positive elements, and not the units, but anyway, that's moderately interesting, but I'm not quite sure I'm not quite sure what the real interest is on this. It must be just as interesting. What you can get in the unital case must be just as interesting.
Yeah.
Is it false in the unital case? Maybe it's still true for projections.
Yeah, you mean that if I use here projection?
Well, it couldn't be true for projections because there only countably many.
Wait,
Sorry, say it again. Which one is countable many?
Well, the projections are countable.
Okay.
So, so for some reason, to get a whole uncountable set, a whole continuum of numbers, you're looking at non-projections.
Mhm.
But it's not quite clear what the
So
fundamental interest is of non.
So two things. So I want to just, first of all, I want to just to make it clear. So here, it means that the image, so just not to get confused, it means that the range of this function is equal to this, right? I hope that is clear. So the other point is that suppose that, okay, give me a number eta in let's say 0 and infinity. So then based on this theorem, I can find the full elements A in this CU of A such that RC of CU of A and this full elements is going to be eta.
same thing, you just rewrote the same thing.
Yeah,
Yeah,
I just,
so that was,
but one thing that because you said that your CSR algebra is fixed, and I'm saying that because actually the point is that this CSR algebra this element is full. Therefore, the hereditary CSR algebra generate. No, this is full.
That's not the hereditary sub-algebra. Not the hereditary sub-algebra.
Generate. This is a full element. So A is full. Agree?
That's got nothing to do with hereditary sub-algebra.
what?
It's ideals.
Ideals?
So sorry. A is full, right? Agree on that?
Means the ideal it generates.
The ideal,
Nothing to do with the hereditary.
yes, okay, yes, that's right. So this means that the ideal generated by A is, or maybe even a stabilized of S is equal to A, right?
So that's the ideal. Well, oh yes, that's the ideal. Sure.
So,
Yes, but anyway,
so therefore, this means, okay, this is what I wanted. Therefore, this is CU actually of A, right?
But anyway, what does it come down to? Was it you or not who was talking about non-isomorphic algebra?
I think. So, okay, yeah, I think there is a theorem by that we can somehow manufacture so many non-isomorphic CSR algebra and outer actions on any finite group such that.
That's fine, but if they want them to be, you like to have unital algebras, Well, the only non-isomorphic unital algebras you get would be counterweighted. The only way this would give you non-isomorphic algebras parameterized by a continuum is if you allow the non-unital
So I'm not talking about non-unital. And if I consider this unital, so it gives you an
you would have to-
uncountable.
You would have to be if you're talking about the distinct isomorphism classes. Talking about isomorphism classes instead of just the values of the relative radius of comparison, then you would have to stick to well, of course, they're all. If you allow non-unital, then you get the whole continuum.
So the non-unital is like what we did together. So it's for cross product, and then we compute the non-unital version is exactly like what we did together. So in our joint work. So you consider non-unital CSR algebra, and we compute even the radius of comparison of cross product for any non-unital, even a stably projectionless.
I'm in favor of non-unital. I don't mind non-unital algebras, but are you talking about non-isomorphic algebras or not?
Oh, no.
You're not talking about non-isomorphic.
No.
But with you, that mentioned Chris and Iran's paper.
Yeah, okay. This is their case is unital. They consider non-isomorphic unital CSR algebra. I think the counterplementing, I doubt. But okay, we can look it up. So I think that they found, I think, uncountable class of such CSR algebra.
I only remember two.
There are two, but the number is different. So this number, because the number for this radius of comparison is in the inner wall. So, and for each number, they found a projection. Therefore, is uncountable. I believe is uncountable.
I don't think. So, but are you saying that? So, okay. So, my understanding, the interest in Chris's and Ilan's examples is that they presented examples of C-star algebras which have the same invariant, the same radius of comparison, but are not isomorphic.
Yes.
So, did you do that? And does this here imply that you kind of come up with more examples like that?
Yes.
Can you explain
Because
that?
if you take this CSR algebra in their paper, right? So, and the radius of comparison for this CSR algebra is R, right?
Sure.
So therefore, you can find another full elements in which the range of this can be here. They just prove this theorem.
What are the non-isomorphic algebras?
What do you mean?
What are the non-isomorphic algebras?
So this is kind of, you should check the instruction. This is kind of part of the Wilson algebra.
Not an answer. I don't understand.
So they construct based on the standard method, a Wilson algebra, and they compute the radius of comparison.
I'm familiar,
Right?
familiar with their work.
Yes.
I'm forgetting now all the details. It was a while ago, but I'm asking about this result. Like,
Right.
Does this result tell me that there are actually more examples of C-star algebra satisfying those conditions?
Not more CSR algebra, but you can say that you can find uncountably many non-isomorphic CSR algebra which has a stable rank 1, same Elliott invariant, and the range of the radius of comparison function is even this, not just single number.
That sounds like two statements.
So you remember what they proved? They proved they proved that there's an uncountable family of CSR non-isomorphic CSR algebra.
Sorry about the uncountable part.
Okay.
Two already is good enough.
So,
You
okay.
found two C-star algebras with the same Elliott invariant, the same radius of
Radius of
but which are not isomorphic.
Right.
That's already an interesting result.
What I'm saying is that just in their theorem, add with the same with this not with single radius of comparison, with this full range of radius of comparison function, but those are not isomorphic. right? Just take the CSR algebra they already constructed in their paper, right?
Okay.
Take
Those are
there.
constructed-
So then you have this, right? Then you have this. You have this.
Yeah, they have the same radius.
So
right?
then by this theorem, just manufacture all full elements such that the range is this.
Okay, and what, and then what?
So that's it.
A priori, that doesn't say.
I mean, the non-isomorphic part, they already proved there, right? I can give you many examples of non-isomorphic CSR algebra, but those are not, they don't have necessarily same Elliott invariant. For example, I can prove this for any,
If you don't have the same Elliott invariant, they're clearly not isomorphic, right?
yeah.
I'm still a little lost.
I have a very simple understanding of
Mhm.
the non-isomorphic thing, and I wonder if it's correct. So for the, I've forgotten the exact details of the paper of Chris and Milan, but what I remember roughly is it's a very precise statement. They construct some unital C-star algebra. It's not exactly it's not a Willison algebra. It's a modified one.
Yeah.
And it has projections, and it's a unital. You look at the unital algebra to begin with, and then you stabilize it.
Yes.
And then but you keep track of this projection.
Yeah.
And if you look at different other projections, then you can then they show that those can have different relative radii comparison for the same algebra.
Yep.
But then if you cut down to one of those, then what used to be just called the relative radius comparison of the stabilized algebra, say, with respect to this fixed projection. If you cut down to this other projection, then that's the unit of that cut down algebra.
Yeah.
So the standard radius of comparison of that unital cut down algebra is this quite different number, which is the relative radius of comparison for the original algebra. So for all the different projections, you get different
Yes.
different numbers, but only countably many for fixed overall construction. All right, but that's my understanding.
Yeah. Except the
And
countably many, I
in this
agree.
case, in this case, you would get uncountably many, but they'd be non-unit.
Yeah.
Because you're cutting down basically the ones where the full elements, which are non-productions, with the cut down algebras, with which. So now you'd be introducing the idea of for non-unital algebra, you have a sort of a particular radius of comparison defined with respect to the strictly positive element of the algebra itself,
Yeah.
which is not a projection. It's sort of elevated above the. Maybe you wouldn't call it the relative radius of comparison, you just call it the radius of comparison. That's my understanding.
Yeah.
Well, anyway.
Yeah.
The reason I'm harping almost on this question of isomorphism is that at the moment that seems to me that aside from the technical interest of this study, that seems to be the main reason for considering.
Yeah.
But anyway, the technical aspects of it are interesting themselves. People looking at sister algebra theory.
Yeah.
But sometime we'll be happy to see more of the technical side and actual calculations and proofs.
Yeah, sure.
Yeah,
I think that we are running out of time. Yeah.
No, time is.
Yeah. But energy is not.
Spoil the conversation.
Sure.
We're just reaching a natural point to postpone the discussion.
Yeah, sure.
But maybe just one, he could just, I
Mhm.
think if I want to prove something, so. I think I can imagine how you prove that theorem.
Mhm.
For this theorem, I also have an idea, but I don't-
For
I'm
this
not sure
one?
if it works, but so can you explain briefly how you get that? So you have you fix your radius of comparison.
Yeah.
I give you a number between 0 and infinity.
Yes.
And how do you produce a full element? So you're.
First of all, the 0 is easy. The answer of 0 is 0. So now, yeah. Now, okay, here is actually the art of the positive answer to the rank problem. So what do you want me to remind you the rank problem? Okay, let me just quickly. So the rank problem is basically this, that when this map is surjective. So, right? So here we have S, and here we have lower semi-continuous strictly positive affine function, right? So, and here is the question that when this has a positive answer, so in the stable rank 1, so the answer is yes, this map is surjective. So now, suppose that you have eta in 0 and infinity, right? Infinity. Now define this function.
Yeah,
Yes.
I wanted to, that's what I think. Yes, yes.
Yeah.
I know what I want to
Okay,
see it.
but, you need any help?
No, I don't think so, right? So, oh, okay. Okay, that's it.
So I mean,
Okay.
now here you define this affine function from.
No,
Uh,
I think the drift is convincing. I think I know.
Yeah. Okay.
But, okay, can you do it without stable rank?
Oh, okay. If they answer the
Stable rank one, it becomes kind of easy, no?
if I don't know. It's not clear. There is a function, because at the end of the day, I want to find a full element such that lambda of A is equal to eta for all lambda.
Yeah,
And I don't know whether in general I can do it or not.
but that's the interesting. So that's an interesting question, right?
Yeah.
But I mean, it might be equivalent to the rank problem, right? Like, it
Yeah.
might be somehow, maybe if it's not surjective, then you can somehow conclude that the image will necessarily lie somewhere.
Yes, I think I can say that if the answer is yes to rank problem, so we can do that. But there is still one. I mean, that only rank problem doesn't solve the problem. You should also use that theorem and rank ratio function. Because rank ratio only give you one number and one full elements, and now you have to compute the radius of comparison. I think you have a version of my draft. At some point, I send it to you. So
I can't say I read it, but
yeah, you can just.
I was busy. I had a lot.
That's fine. Don't worry.